Hello, and welcome to lecture 4 of the Deep Learning for NLP course. Today we talk about text representation. In this lecture, we mainly talk about common features used for converting textual data into numerical vectors. And then we discuss basics of word embeddings or embeddings in general. We will see how we can get these embeddings and where should we use these embeddings and how to use these embeddings. And at the end, we will see some limitations of existing word embeddings, which are still open for further research. As always, let's start with some recall from the previous lectures. The input to a supervised learning algorithm is a training set to which we refer as X and Y, where X shows input examples and Y shows corresponding labels. The goal of a learning algorithm is to return a function named f that accurately maps input example to their desired label. So if we are given a data set like X and Y, the task of the learning algorithm is to return a function like f that maps X's to Y's. So this is the main concept behind any learning algorithm. Okay. But if we are talking about neural networks, the input to neural models, which is f, should be a numerical vector. But as we know, in many NLP tasks, the inputs to these functions are usually text. So as the raw data, we usually receive some texts, but we want to do some classification on this text, right? For example, we receive the text of an email and we want to say if the email is a spam or not. Right? So it's very important that we know how can we move from input texts to some vector representation of these texts. Why? Because we know that the input to any learning algorithm or the input to any neural model or any classifier is a vector of numbers. Now we ask the question, how can we represent texts via numerical vectors? That's why we will talk about text representation. Text representation is also known as feature extraction. But it's very important to know that we don't want to move just from text to some random numbers. We want that the vector representation of the text captures some linguistic properties of the text. So these numerical vectors should represent some semantics or linguistic properties that we can easily understand by looking at the raw text. So we define a function named feature function. This function receives a text and returns a number, or receives a text and returns a vector of numbers. And then given this vector like x, we can feed this vector to any neural model or to any classifier or to the output of any learning algorithm. So in this lecture, we focus on feature functions rather than learning algorithms. In lecture 3, we discuss about learning algorithms, and we have seen how we can train a neural model using backpropagation, and how we can remodel or recast a machine learning algorithm as an optimization problem. So if you are not sure how we should train a neural model or how a learning algorithm works, make sure that you watched and read all the slides. I watched the video and read all the slides of lecture 3. Because in this lecture, we mainly focus on mapping text to some vectors because we assume that we know how a learning algorithm works. Okay. But before going forward, in order to know that in order to know that our feature functions capture the linguistic properties of the text, we need to know, okay, what sorts of information exists in a piece of text, and how can we then map them to some numbers. So now we focus on different aspects or different linguistic aspects of the piece of text, and we will see how can we look at them as source of information, or what sorts of information do exist around the text. The first part of, okay, in order to do this, we need to talk about some terminologies. First, we want to talk about letters. Letters or characters are simply the smallest units in a language. Like in English, we say A, B, C, D, and so on, right? So this is the smallest unit in a language, and probably the first source of information that you can get from a piece of text. Now we want to talk about tokens and words. Tokens are outputs of a tokenizer, and words are meaning-bearing units. It's very important to know that there is not a unique definition for words or tokens. There is a big debate in linguistic theories and like big discussions in every community about the meaning of words and the meaning of tokens. But from the machine learning point of view, we can simply think of words are meaning-bearing units, right? And tokens are the output of a tokenizer that exists around the world. And since in this course we are focusing on machine learning part or deep learning part, not the linguistic part, so we use the term word and token interchangeably. Okay, now we can talk about lemma. Lemma is the dictionary entry of the word. So if we have, for example, a word booking, the lemma of the booking is book, right? Or book has the lemma book, and books has the lemma book. So book is the lemma of different shapes like booking, book, and books. Okay, how to obtain lemmas? Use some morphological analyzers. They are available for many languages, so they work pretty well. But the point is that if the point is that they work pretty well if if there is no misspelling in the word, if your word is correct. But the point is that if you have a small mistake, if a small dictation mistake in the word, then your morphological analyzer fails. That's why we usually don't use lemma, and we usually use a stems. What is a stem? A stem is a short version of a word defined based on some language-specific heuristic. For example, picture. For example, this word, picture, something I cannot pronounce it, is the stem of pictures, picture, and picture. So as you can see, the output of a stemmer need not to be a valid word. So, but the point is that this is the smallest unit of a word that is common among different morphological versions of the word. The good thing with stemmers is that they work even if there are some misspelling in the words. So that's why we usually use the stems. Okay, we talked about, okay, so now we know what about letters, tokens, and words, lemmas and lemma and stems. The most important part here is tokens and words, which can be easily obtained by some tokenizers. The simplest tokenizer in the world, just like at least for English, is separating tokens based on white space. So if you have a sentence and a split words based on white space, so you easily get tokens in that sentence. But the story is not easy because we have some words like New York, which contains one space between New and York, but it is not two tokens. It is not two words. It is one word because it is the name of one city. Okay, but as I said, the story is very very broad, and we don't need to take care of the details of the difference between tokens and words in this lecture, because currently there are a lot of tokenizers that work perfectly fine, so we don't need to take care of that for now. So, and it's more or less about natural language processing rather than usage of deep learning for NLP. Okay. The other source of information is lexical resources. These resources provide some information about words and their relations. Let's think what type of resources can we get to find the relations between words. The first type of lexical resources is dictionaries. The second, which I guess everybody knows what dictionaries are. Now, the second lexical resource is WordNet. WordNet is designed for English, and as the name shows, it captures the relations between different words in English and model these relations by a graph or a network. In this lexical resource, each word is associated with one or several synsets. But what are synsets? Synsets are linked to each other according to semantic relations between the words. Synsets are simply a set of words. So for each word, each word is associated with a set of words, and this set is named synset. And this synset, on a synset of different words, are connected to each other according to semantic relations between the words. What do we mean by semantic relations between words? We have different sorts of relations, like hypernym, which is this word is a more specific version of the other word. Right? For example, Mercedes Benz is a more specific version of car, right? Or SUV is a more specific, is a hypernym of car. Hyponym is less specific. So car is a hyponym of SUV. Antonyms are clear. Holonyms are part whole. For example, a wheel is holonyms of car, and meronyms is like whole part relationships, like car, meronyms, wheel. WordNet also contains information about nouns, verbs, adjectives, and adverbs. So it contains different types of words. So it's not only about nouns, or it's not only about verbs. It contains different types of words. So it's pretty rich resource for finding relationships between words. The good point about WordNet is that it's manually created, so it's very precise. It's not only it's rich, but it's also very accurate. So you can rely on the information that you extract from WordNet. But on the other hand, the weakness is that it has a very low coverage, because when you hire human beings to do, or human experts to do some tasks for you, like for example finding the relationships between words, it gets easily very expensive to cover a lot of words. So you can easily find many words that do not exist in this lexical resource. FrameNet is another. FrameNet and VerbNet are another lexical resources for English. They usually focus around words, verbs, and they are also manually created, so they are also very precise, but they mainly focus on verbs and like what are the arguments of the verb and so on. Paraphrase database is also another lexical resources that it goes beyond words, and it tries to find two expressions in the language of paraphrase or not. Yeah, and it contains paraphrases. And this one is automatically created, so we expect to see some noise, but on the other hand, we cover some, we have a good coverage over different paraphrases. Okay. But why did we talk about these resources? Because these resources are just like these source of information helps us to find good information from text. So now we want to know what information can be extracted directly from a word, as an example. So let's say we are given a word and we want to know what information can be extracted from these words. As we discussed, we can easily look at letters and see the word comprises of which letters, right? And some people can say, okay, so the order of words can matter as well. So like, for example, the word dog and God, they both have the same letters, but the order of the characters are different, right? So letters comprising a word are the same, but the order is different. So we can focus on letters. We can also focus on the length of words, in terms of meaning that how many characters or how many letters consist in a word. And we can check the first letter is capitalized or not, because we know that for some languages like German, all nouns should be written, or all nouns should start with a capital letter. So it's important to know or that the first letter is capitalized or not. And we can also check if the word includes hyphen or not, and something like this. So any of these questions can be taken as a feature function, right? So you can define feature 1 as length of word. It takes a word and returns its length. You can define another function for checking if the first letter is capitalized or not. So it returns a value 0 or 1. 0 shows that the first letter is not capitalized, and 1 shows that the first letter is capitalized, right? So the output, any of these features can be taken as a function, to which we refer as feature function. Okay. But if we go beyond the word and we assume that we are given a text like a sentence or a paragraph, then what sort of information can be extracted from this piece of text? The count of each word in a text is taken as a feature, right? So in this method, we refer to our features as bag of words. So we say if we have a piece of text, we assume that we put all of these, all words appear in this text in a bag. So when you put some items in a bag, you usually don't have any order between the items, right? So we put all words in the bag, and just we take one word out and we say, okay, this word exists in the bag. So right, so then the value is 1, and then we pick up another word from the bag and we say, okay, the word exists or not, and the value is 1, and if it is already seen, just we increase the frequency of that word, right? So usually the bag of words works like this. So you look at the words that you have in a text, and you count how often you see the word in the text. So for example, I love in this figure we have I love this movie. So we look at I, and then we start counting how often we see that in the text, right? So and then we map this number to a feature, to a value. So as we see here in the bag of words feature a method that that maps a text to a vector of numbers, each feature function is a word that appeared in the text. So for example, here so let me use my pen. And yeah, so here, oops. Okay. Here I appeared 5 times. 1, 2, 3, 4, 5. 5 times. So the feature function I returns 5. We have another feature function named and then we start counting how often and appeared in the text, right? 1 time, 2 times, and 3 times, right? So and appeared 3 times. So in this way, each feature function is each word that we have, and the value that each function returns is the frequency of the word in the text, in the given text, right? In this way, you can easily map a text like this to a vector like what we can see on the right side. So the backup word is a method that takes input text and maps that to a vector of numbers, and each element of the vector is the frequency of one word in the text. Okay, what is really clear here is that backup word does not care about the order of words. So it only cares if a word exists in the text or not, and if it exists, then how many times the word happened in the text. But it doesn't care if I and love came next to each other, right? So, and that's why it's called bag of words, because you get a text and put it in a bag. So, and then you pick or you take one word out from the bag and start counting this. But you don't care actually the word is the first word in the text or the last word in the text. Another feature that we have is, or another way to represent the text by vector is TF-IDF, which stands for term frequency and inverse document frequency. Let D be a document from a given corpus. We map word W of document D to a number as follows. So we start counting how often. So let me use my pen again because it's easier to talk about it. So what we do is that we start counting how often a word occurred or appear in document B, and we normalize that to not get biased towards the length of the document, right? So this part is exactly what we do in bag of words, right? Our term frequency. So this is exactly TF. And what is the right part? The right part is IDF. So it goes for inverse document frequency. But we know that if a word occurs in all documents, then probably it's not a good word to distinguish them, right? So for example, if you want to distinguish between spam emails and emails that are not spam, you probably need to look at the words that occur in one set, like the words that occur in spam emails, and the words that do not occur in spam emails, right? But the words that occur in both categories, they are not very important, or they are less important than words that appear in one of these sets. So we check for how many documents or how many documents do we have in the corpus, and how many of these documents contain word W, right? If word W occurred in all documents, so then the numerator and denominators are equal, right? Then we have for the second term we have log of 1, and log of 1 is 0, and the value of this feature is 0 because the word is not discriminative. We have a word that occurs in all documents, so it's not an informative feature to distinguish different documents. So given TF-IDF, we not only care which word occurred in which text, and we not only care how often a word occurs in which text, we also care about we also care about words that occur in fewer texts are more important because they contain more discriminative information. Okay. So as you can see here, TF-IDF is very useful when you want to discriminate between different input texts. And the other important factor that we should consider here is that we started from letters. So we assume that we have one letter, and then we went one step up and we discussed about words. So we said, okay, so let's assume we have one word and what features we can extract from the word. And now we are in the level of text. So we said, okay, we can use bag of words. But now we said, okay, but you can go even one step further and look at the whole corpus. So not only looking at words in one text, you also look, okay, how often the word appeared in other documents. And if it appears in a lot of documents, in many of documents in the corpus, it is less important. But if the word occur in a fewer documents in a corpus, this word is more informative for the given corpus. Okay. We only think, okay, but the point is that none of these methods cares about the order of words, right? For example, in bag of word or in TF-IDF, we don't care where the word happened in the text. We only care if the word occurs or not, and if so, how often. How can we involve some ordering information? It's very easy. So you can say, okay, why should we only care about one word? So we can also count two words, right? So instead of using the frequency of one word, we use the frequency of n sequence of words. So instead of using one word, you can look at two subsequent words. If you use two subsequent words, these features are usually named bigrams. And if you use three subsequent words, these features are usually named trigrams. So let me go to the bag of words slide. So now we can, instead of extracting, let me pick up my pen again. So instead of extracting one word, we extract two words, right? So this is like a bigram. So we have I love, and instead of having I here, we count I love. So we say how often I love happen in a text. So probably only one time, right? I don't know. I mean, I didn't count, but probably, yeah. So when we look at the text quickly, it seems it happens only one time. So this is the benefit of using n-gram, that you can include orders. But do we need to only consider 1 gram or 2 grams or bigrams or trigrams? No, you can. There is no limit on n. You can also use them in combination. So you can use a frequency of words or frequency of bigrams, or you can use frequency of words plus frequency of bigrams together. So you can have as many features as you wish. So there is no limitation on that. Okay. Okay. So let's talk about another source of information. Each of the other source of information that is really important in NLP is context. Each piece of text occurs within a larger text, which is known as context. The point is that when we discuss about bag of word or TF-IDF, we kind of ignored the context. Even when we go for n-gram, we didn't look at the context. We just look at how often two words occur next to each other. But we know that these two words occur usually, or the one word occurs usually within a sentence, right? And we usually understand a word in a sentence, or even in a text, or we understand a sentence in a paragraph. How should we encode contextual information? The easiest way to encode the contextual information is to use position of a word within a sentence or a document. You remember the example that we have, like I love something. In this example, like when we use bag of word, we only count how often word I occur in the sentence, right, or in the paragraph. But we don't know if the word is the first token in the sentence or is it the last token. How can we capture that? Just we can define a feature function that returns the position of the word in the sentence, right? So this can be easily a function. But why should we only use the position? We can also look, okay, what word appeared before this word and what word appeared after this word. So we can define a feature function that takes a sentence and returns the word before and the word after the target word. This is what we call as immediate context, a window of keywords surrounding the target word. Let's assume that we have an example like the cat sat on the mat. So we give it to a feature function like f, and we ask that to return words or return surrounding words in a window of length 2. So it returns word -2 is the, word -1 is cat, and word +1 is on, and word +2 is the, right? So a feature function can easily take a sentence and a word as a target word and the length of the window and returns the surrounding word of this target word as contextual information. Good. But okay, what's other source of information we have, we know that context is not only about the surrounding words of a target word in a text, but language also has some relations with other words in the language in general. For example, we know that there is a relation between patient and the doctor, right? There is a relation between doctor and hospital. So without looking at any text, as a human being, we have this knowledge, this background knowledge between words in our minds. And we also know that there are some lexical resources available that provide such information for us. So we can use this source of information like lexical resources to extract other types of relations between words. For example, we can easily check if a word in a list of common if a word is in a list of common person names in German. So we can assume that we have in the background knowledge, we keep the list of all common person names in Germany in a file, and given a word and this function, given a word and this file, a function can check if the word appears in this file or not, right? So we can define a feature function that easily or that easily returns 0 or 1. 0 if a word does not appear in the list of common person names in Germany, and it returns 1 if a word is part of common person names in Germany. Okay, another feature could be like, is a word a female or male person name, or in other languages like German, we can check if the word is masculine or feminine or neutral. No? Or we can have a feature function that takes a word as an input and returns as the output, it returns masculine, feminine, or neutral. We can check the lemma of the word, we can check the stem of the word, and we can ask what information do lexical resources give us about the word, like what are the synset of this word, right? What are the synonyms of this word, and so on. Okay, so we discussed that the output of a learning algorithm is a model or a function like f. F takes as input a vector x with dimension d in, which is like the dimension of the vector, like how many elements should we have in this vector. And f returns as output a vector y hat with dimension d out, which we usually refer as output of the network, right? How can we map? Okay, now we're gonna focus on textual features, and now we want to know how can we map textual features to a vector. We always discuss like we can define different types of features. Usually we can have numerical features that you map a text to a numerical value. For example, the bag of word algorithm maps a piece of text to a vector of numbers, where each number shows how often a word occurs in a text. The second category of features is categorical features. In this set, the value of a feature is from a set of values. For example, when we ask what is the part of a speech tag of a word, it is the value of this. The value of this feature function is not a number, but is one value from a set of possible values. For example, when we say what is the type of a noun in German, or what is the gender of a noun in German, the output could be feminine, masculine, or neutral. So the output is a category. So this feature function is a categorical feature because the output is not a number, but is a category. For numerical features, we do not have any problem. Our goal is to move from text to some numbers, and numerical features do this for us. So we start from the text and they return some numbers. We are totally fine. What should we do with categorical features? They return some categories. They do not return some numbers. There are two solutions to map categorical features to numbers. The first one is one-hot encodings, and the second one is dense embeddings. Let's go to one-hot encodings. Let's assume that values of a feature is in categories V0, V1, and V2. We encode the space of feature values via vectors in which each entry is either 0 or 1. Each entry is associated with one of the categories, and only one item in a vector can be 1. The rest should be 0. Such a vector is named one-hot vector. So the way that we introduce this categorical space, or the space of feature values, is via 3 vectors. So for category 0, we use 1, 0, 0. So let me again use my pen. So for category 0, we set the first element in the vector to 1 and the rest of the items to 0. For the second items in the category, we set the second element to 1 and we set the rest elements to 0. And for the third category, we set the third element in the vector to 1 and rest to 0. In this way, we have one hot vector. We have vectors in which only one element is 1. And the rest of the items or the rest of the elements are 0. 0. 0. Okay. Let's look at some examples. Let's assume that we are given a text and we want to predict what is the topic of the text. So our model is function f that takes a vector x. Let's say we have a vector representation of the text and returns a y-hat representation, the topic of the text, which can be from news, sports, science, politics. So we have 4 categories for a topic of a text, and we want to predict which category it is, right? And the point is that the output of the network here is also text, so it's news, sports, science, politics, right? So we need to map these texts to some vectors. It is a categorical feature, so how can we represent categorical features or categorical labels? There are 2 ways: one-hot embeddings or one-hot encodings and dense embeddings. Now we talk about one-hot encoding. We map news to a vector, to a one-hot vector, where the first element is 1 and the other items are 0. And then for export, we reserve the first element for news, right? So we set the second item or second element in the vector to 1 and the rest to 0. And for science, since we use the first and the second elements for news and export, we use the third element for science and we make it 1 and we set the rest to 0. And for politics, we used a vector like this, right? So in this way, we can represent the text news with a one-hot vector, text support with a one-hot vector, and politics with a one-hot vector. Okay. Can you think of what the length of one-hot vectors is for a feature with k categories? Let's say in this example we have 4 categories, right? So what would be the length of the vector? Yeah, the answer is easy, right? So the answer is K. So if we have K features or K categories, the length of the vector is also K, because for each category we need one element. So if we have K categories, we have K elements. K elements. Okay. Let's assume that or as another example, let's say V, or the set V, shows vocabulary of a language. We can take V as categories a word can take in the text, right? So words can be encoded by by one hot vectors. Okay, more formally, let's assume V is a set of V0 to V whatever length and whatever number of vocabularies that we have in a language. We can show one word in the language by a one hot vector like this, right? We can show the second word in the vocabulary by a one hot vector like this, and the last word would look like this in some numbers, right? In this way, we can easily represent the text by a bag of words and then represent each word in bag of words with its one hot vector. So we can say which word appeared in the text, and for example, word I, and then we say, okay, I is the third vocabulary in the language, and we just use its one hot vector to represent I with a vector. Okay, so now the point is that how can we define vocabulary V given a corpus D? We are given a set of documents, or for a language, we are given a million of texts in one language, in English, and we are asked to define the vocabulary of that language. How can we define, or how can we extract all vocabulary, or a set of vocabularies given a corpus D in a language? I want you to pause the video for 1 minute and write your answers in the comments. Either if you are watching the video in YouTube, write your comments in YouTube, and then I will be back and we can talk about the rest of the lecture after 1 minute. Okay, so let's get started again. I hope you had enough time to write your answer to the question that we have in this slide. How can we define vocabulary V given a corpus D? Okay. Let's look at some properties of one-hot encodings. We can easily notice that for a language that has 4,000 or 10,000 or 10,000 vocabulary, word vectors can get easily large and very sparse. The other weakness of one-hot encodings is that semantic relations between words are not encoded in word vectors. We only know which index of a word vector is associated with one word in the vocabulary, but we don't know if given vector representation of two words, we cannot check if the words are related or not. Therefore, it's better to use one-hot representation for a few distinct features, like the categorical labels that we had in some previous slide, where we expect no correlation between features. So it's better to use them for features that are categorical, but the size of the size of the category set is small, and also you do not expect any correlation between features. For example, you do not expect to see any correlation between sports, science, and blood, politics, title, and topics. Um, okay. In order to overcome these weaknesses, we can use dense encoding. The main idea is that a categorical feature uh, can be embedded as a vector in a d-dimensional space. So assuming categories C, C0, C1 to C, given the number of categories that we have in set, the size of the vector or the dimension of a vector representation of each category can be limited to any size that you want. So it can be 4. So it doesn't need necessarily be the number of categories that we have. So it can be any smaller value. So if you want to represent each category by a vector with length 4, so we can just assume that C0 is assigned with this vector, C1 assigned to another vector, and the last category is assigned to another vector. So the point is that you represent each category with just a vector of numbers with length d. So very easy. So if we have like a vocabulary set, so instead of representing each word in the vocabulary with a vector, with a one-hot vector, where only one element is 1 and the rest of the elements is 0, we use a vector of dense values or real values, but we make the vector quite dense and reduce the dimensionality of the vector. So instead of defining a vector of length 10,000, because, for example, we may have 10,000 words in the vocabulary. So we define a vector with size 4, and we fill the vector completely. So we make the vector dense. Okay, but what is the best size for any encoding and for dense encoding? There is no rule of thumbs for that. So you can assume that the size of the embeddings or the size of the encoding is like a hyperparameter. So you can define 1, 2, 4, or 300, 400, 500. The point is that the larger vectors you use for representing your vocabulary is more likely that you capture more information about relationships between words. We will discuss about that in the previous slides. Okay, in the one-hot method, we represent each word with a sparse vector of size v, or the absolute value, or the size of the v, or the size of the vocabulary. And in dense encoding method, we represent each word with a dense vector with a small size d. So this is the main difference. So instead of having a sparse vector but a very, very large vector, we use a small, very short vector, but we make it dense. So we don't use sparse vectors in dense embeddings. Okay. As we discussed, in dense encodings, the dimensionality of vectors is d, and when we are training our model, we use this use these vectors as some parameters in the model, and during the training we update these parameters. So the parameters the value of these vectors will get updated such that vocabularies or features that have similar properties in a language will have similar properties in the embedding space. So it's mainly useful when we expect some correlations between features. For example, we expect that cat and dog are semantically related, right? Because we expect that cat and dog be semantically related because both of them are animals. But if you use one hot vector, you don't see any relationship between these two. But if we use some dense representation and use these vectors as some parameters in our neural model and we update them, then these vectors at the end of the training capture some relations between these two words such that they can solve the task efficiently. Dense encoding is also useful when we have a large number of features like vocabulary in the language, right? Because when we have a large number of features, feature values or categories, using one hot vector means that you are going to use a very, very large vector, while most of the elements of this vector is 0, right? So instead of using one hot vector for features that have a lot of categories, you can use dense encodings. Okay. Now that we know what is dense encodings, we can talk about embeddings. By embeddings, we mean representing each textual feature as a dense vector in a low-dimensional space. So the embeddings and dense encodings are kind of similar, and just embeddings are mainly used in text representation to say that you map each feature in it, each textual feature to a vector of to a dense vector of numbers. But how should we define these dense vectors or embeddings? Now we can talk about a specific type of embeddings named word embeddings. As it's clear from the name, by word embeddings, we want to represent each word by some dense vectors in low dimensional space. Word embeddings are dense representations of words in an embedding space. But how to obtain word embeddings? The first answer, or just how to should be obtain a dense representation for each word in the vocabulary. The short or maybe the first answer is to randomly initialize word vectors. So what if we just randomly say, okay, this vector should be assigned to dog, this vector should be assigned to cat, this vector to eye, this vector to love, and so on, right? And then we use these vectors as parameters in our neural model, and we fine-tune these parameters during the training of neural network. In this method, or that I've just described, is named random initialization, which is one of the fundamental steps in mapping words to word embeddings, or in order to obtain word embeddings. And it's called random initialization step. So in this step, we initialize the embedding vectors to random values. But I mean, we can do that in different ways. Like values are uniformly sampled from numbers in different ranges. Some people can say, okay, let's extract the values from -1 to +1 uniformly. Mikolov has shown that it's better to extract the values between -1 divided by 2 times the dimensionality of the vector. So if you want to have a vector of 100 dimension, you want to have a dense vector with 100 elements, or the length of the vector is 100. So you need to use the range of -1 divided by 200 and +1 divided by 200, right? So somehow Mikolov believes that it's better to relate the values of the vectors to the length of the vectors. There is another type of initialization named Javier initialization. In this method, the range of the values that you sample your vectors is defined again based on the length of the vector, and it's defined like this. These two are just most common approaches to initialize word vectors randomly. So it's obtained by some experiments and practice. But this is only the initialization step. And after that, we can use these vectors and as some parameters for any neural models, and we tune these parameters for any NLP task. Right? So if you are doing, for example, name entity recognition, just you can use it for name entity recognition. If you are using you are solving summarization, you randomly initialize word vector and then you solve the summarization task. However, we as human beings can define semantic relations between words independent of any NLP task. For example, we know black and blue are colors. We know dog is more similar to cat than to chair, right? We know easy is the opposite of difficult. And we are not solving any NLP task here, right? So it is only the knowledge that we have about words in a language. And so if we can have this knowledge, the point is that the question is that can we encode this knowledge into dense representation or into word embeddings? Or in other words, how can we find word embeddings such that vectors of words with similar meaning be close to each other in the embedding space? So if, for example, dog and cat are semantically related, then the vector representation should become close to each other in the embedding space. Okay, in order to go in this direction, we need to have a clear understanding of word meaning. Fritz says that you should know a word by the company it keeps. I want to illustrate this phrase by a chessboard in which each piece doesn't have a meaning unless you interpret that piece in the context of other pieces. So you need to consider, or you need to have a clear picture of all pieces in the chessboard, and then you then can interpret the role of each piece in the board or on the board. This is the way that we can have a meaning for words. So in order to obtain some meaning for a word, for example, easy, or for a word difficult, we need to read a lot of texts, right? So we read a lot of texts, and during time we learn that easy is opposite of difficult, right? Easy is an adjective, and difficult is also an adjective. And somehow we have a meaning in our mind about easy and difficult, but this meaning is usually defined with respect to other words in a language, but not because of the text that we are seeing, but because of many texts that we have read during our life, right? Okay, so given this word meaning that words are not independent, so you should interpret words with respect to what they accompany them. Now we can come up to distributional hypothesis. So that words that occur in the same contexts tend to have similar meanings. Now, this distributional hypothesis is like a hypothesis that we make to encode semantic of words in with some vectors or into some vectors. We assume that words, so we hypothesize that words that occur in the same contexts tend to have similar meanings, or they have similar, or they have related meanings. How can we model the distributional hypothesis? So, and now given this hypothesis, we should try to model that. The first idea is to use word context matrix. So if we are saying that words that occur in a similar context should have similar meaning, so we can define a matrix over words and contexts, and then we check how often a word occurs in a context. And this method is named word context matrix. We count how often a word has occurred with a context in texts from a large corpus. Context is defined by a window over words. So let vocabulary set V be the set of words in the vocabulary, and C be the set of possible contexts. Word context matrix M is a two-dimensional matrix whose rows are associated with V and columns with C. Each entry of the matrix indicates how often a word occurs with a context in the given corpus. This matrix is also known as a co-occurrence matrix. So in word context matrix, let's look at a simple example. Let's assume that our corpus contains 4 sentences. I like deep learning, I like NLP, I love machine learning, I love NLP. And we define window size 1. In reality, window size is larger than 1. So they define it like 10, 15, 20 or something. Okay, then we define a matrix where rows are words and columns are contexts, and each entry shows how often a word occurs in the context of on the context of the word that we see in the column. For example, we want to see how often the word I occurs next to the like, right? So here we have 1, and here we have 2. So we have 2. We have seen like and I twice next to each other. Let's say we want to see how often words love occurs in the context of I, right? So we see that I love and I love, so it happens twice. So this is the way that we define word count matrix. And if you do it on the full corpus, and you extract the co-occurrence of each word in each context, you will see that the words like and love have a very you will see that the words like and the word love have very similar vectors. So meaning that the representation of unlike and love will get close to each other after some time. And why is it happening? It's happening because of the distributional hypothesis. We are in the distributional hypothesis. We are saying that words that occur in a similar context usually have similar meaning. So here, if we assume that for target word like, I, deep learning, and NLP are like the context, and love for word love, I, ML, and NLP are the context. So the words like and love are used in more or less similar contexts. Therefore, they should have similar representation. And by counting the co-occurrence of words and contexts, we can easily capture, or we can easily model hypothesis, distributional hypothesis. Okay. Oops. So let me clear my drawings and now we can go forward. Okay. So if we have a large corpus, this is called count-based embedding. So for a large corpus, the size of the matrix is very large, right? Because you have the size of the vocabulary is fixed. Why is it large? Because the number of rows that you have is fixed because it's equal to the number of words that you have in the vocabulary. But the point is that the number of columns that you have is growing exponentially because columns represents contexts. And when you have a large corpus, it means that you have many different contexts. So you have a lot of columns in your co-occurrence matrix. So this matrix can easily get very large. This matrix could be also very sparse because many words do not occur in many contexts. So even when we look at this example, we see that many of elements of the matrix are zero, right? Because many words do not co-occur with many contexts. So when you have a very, very large corpus, you have very, very, very large matrix, and many items of this matrix are zero. So to encounter this, so we need to somehow save this matrix and only capture information that we need. So we can use dimensionality with reduction techniques. These techniques like SVD, they take a matrix, like a very, very big matrix with large dimensions, with big dimensions, and then they reduce the dimensionality of this matrix and return the main information that we need to know about the matrix. Okay, that's a good solution, but what if we add another text to the corpus? Then it means we have a new context and maybe new vocabulary in the language. So as a result, we need to enlarge the matrix again, and we start counting the new vocabulary for the new context, and also new vocabulary for the previous contexts, right? So, and after doing that, we need to apply dimensionality reduction again. So by adding a new word or by adding a new document, we need to build this matrix every time, and we also need to apply dimensionality reduction. So this is not a very wise algorithm. I mean, this is a wise algorithm, but this is not an efficient way to model word vectors. Therefore, in order to solve these issues, we want to talk about CBO method. This method is used to define word embeddings without using count-based matrices or without co-occurrence matrices. CBO stands for continuous bag of words. So the main idea is that if we can use bag of words to represent the text by numbers, so we can use the similar algorithm to obtain continuous representations of words. So as any other algorithm in computer science, our tasks should be defined by defining the input and output. So the input to this task is a context. So the output is to predict a missing word from the context. So let's say the input is I NLP or something like this, and we want to predict what is the missing word between I and NLP. So the output or the gold label is like, right? Okay. In order to formulate this problem, we can map it to a classification problem, right? So saying that if we have for any instance like I like NLP and the output is like I NLP where the output is like, we define two instances, one positive and one negative instance. The positive instance looks like this. So we have I NLP and word like, And the task of our neural model is to say if like is a good fit for this context or not. So if words in the same context should have similar meaning. So we can easily ask our neural model to predict that. So we ask our neural model to say, okay, we have context I NLP, and we have word like. Just tell me if it is a good word for this context or not. Or if we put like here, I like NLP, does it look like a good sentence or not? So since this is a positive sample, the output is 1. And the other set of sample we create is our negative samples. So we say, given this context, like NLP, we put a random number here. So like apple, right? Or just cat, or anything that we want. Anything except like. So we say missing word and NLP, and we want to know if apple is a good fit here or not. So the output here is 0, right? So the task of our model is to say, okay, this sentence is positive or is a good fit, and this sentence is a bad fit or is a negative example. So we can easily map the task of distributional hypothesis modeling to a machine learning task that we are given a context and we want to predict the missing word from the context. So here you see the main difference between the CBO method and the co-occurrence matrices. In the co-occurrence matrix, this is a statistical method. So you are given a corpus and you count. So it is a count-based, so a statistical method to find the dense representation of words. But in the CBO method, we try to solve the problem by machine learning models. So we are saying that given a context, we want to predict what is the next word. So this is a machine learning model. So given an input, we want to map the output, or like we want to find the output that is the best for the given input, right? So here, given a context is X and Y is the missing word, right? So for a sentence like I like NLP, so we can remove one word like and make it like a machine learning problem. And we create two sets of examples, positive examples and negative examples. So we can easily map this task. Then we can easily model the distributional hypothesis by a machine learning or by a deep learning model. Okay. Now, given a corpus of texts, we create two sets. Positive set, to which we refer as D, consists of pairs, context, and words, where the word is W is the correct value for the missing word in the context. So in this case, this is an example of the positive data set that we have I, NLP, and like is the actual word in the sentence that we have in the corpus. So if we have I like NLP, like is the actual value in the context. And negative set D prime consists of pairs CW, where C is a context with a missing word and W is a random value for that missing word. So, and I, NLP, and Apple is one sample of the negative data set, right? Good. So we are given a corpus of texts, and then we extract, for example, sentences or contexts, and we remove one word, right? And we put it next to the context, and we make a positive sample. And then for negative sets, we have the context, and we just randomly pick up a word from somewhere in the corpus, and we put it next to the context. Since the word is selected randomly, this method is this is very likely that the word is not a good fit for the context. This method of creating the data sets or training sample is named negative sampling. Okay. Now we compute the score, estimating similarity between context C and word word W, given context word A, C, and W. So we say that, okay, if we have a context like C, we represent each of these, each word in the context with its word embedding, and then we compute the sum over these vectors. Then we compute the sum over these vectors, and we call that context representation. The point is that if word W is a good match or is a good fit for the context, this is the vector representation of the context, and words should be similar to each other. So we use the dot product between the vector representation of the given word and so let me use a different color. Vector representation of the given word and the vector representation of all words that we have in the context to measure or to estimate the semantic similarity between context and the given word. Yeah, and E is a function that maps each word to its embedding. Okay. So if we are given a sentence like I NLP, so if the given input is something like this, I missing word NLP, so this is our context, C, and this is our word, given word W, and we want to know if the W is a good fit to this context or not. What we do is that we use the embedding of W. So just like, let's say if it is a randomly initialized vector, that's fine. So whatever vector that we decided to have as embeddings for word like, so we use this as the embedding representation of this word, and we use the embedding representation of any word that we have in the context, like I, and embedding representation of NLP, and then we compute the sum of them as the context vector, or the vector representation of the context, and by computing the dot product, we compute the similarity between vector representation of the given word I and the vector representation of context. Right? So the output would be a score, for example, 0.5 or something, 0.5 or something that shows how much context and word are the given word are good fit to each other. Okay. But the point is that the scores can be any numbers, right? Because when you use the dot product between these two vectors, the value of or the output score can be any real number. There is no limit for that. In order to make some limitation on these scores, we can give them to a sigmoid function to map the scores to a probability between 0 and 1. So the probability of y equal 1 equals to like the output of the sigmoid function for the given scores. Okay, but as you know, we want to maximize the probability of. So let me use my. What we want to do is that we want to maximize the probability of all the samples in the positive data set D, right? In the positive data set D. So we know that these samples are positive. These are correct samples. W is a good fit for the given context in this training sample. So we should maximize the probability of being 1 or predicting label 1 for this sample. And for samples that are in the negative data set, we should maximize the probability of assigning label 0, because we know that word W is selected randomly for the content. So it's very likely that it is not a good label, right? It is not a good, actually good fit for the context. So what we should do is that we try to maximize to the chance to predict label 0 for these samples. Right? Okay, but in order maximizing this function equals to minimizing a loss function like this. So we want to minimize the negative likelihood of these values. So the only thing that we do is that we minimize the negative value of the above functions, above probabilities. Okay, now you can easily use a stochastic gradient descent to train this model. Right? You do not have any hidden layer or something. The only thing that you have is one layer that you map each word to a vector. So the only parameters that we have is the vectors that we use, or the parameters that we use in the embedding function that takes a word and returns a vector. But other than that, we do not have any other parameters. So during the fine-tuning, we fine-tune the parameters of, we fine-tune actually the word embeddings that we have. And after several iterations, our words or our word embeddings learn to model semantic similarity between words in a language. There is another method named skipgram. The idea is very similar to continuous bag of word method. The main idea is that we treat words of the context independent from each other. So we assume that we are given again a positive data set and a negative data set. And for any, sorry, let me use my pen. So for any given context and given word, we want to know how probable is that word W be a good fit for context C, right? So what we do is that instead of looking the context as a whole, we try to check how good is word W for any word in the context. So we say that to calculate this probability, we can say this probability equals to the probability of word W being a good fit to any word in the context. And this probability, this inside probability, can be estimated by a sigmoid function over the semantic, over the dot product of vector representation of word and vector representation of the CI, which is any word in the context. So again, in this model, the only parameters that we have are word embeddings, which are initialized randomly. So loss in skipgram method is identical to the loss in the continuous bag of words. So again, to try to maximize the probability of samples in the positive data set and to predict label 1, and for the samples in the negative data set, you want your model to predict label 0 because they are not good fits. And then we fine-tune parameters using a stochastic gradient in this method. And at the end of the training, we will have some word vectors that capture semantic similarity between words. Continuous bag of word loses the order information between contexts element. Why? Because why is it so? Because the way that we calculate the score is like we multiply the embedding representation of the given word by the sum of the all words, sum of the embeddings, sum of the word embeddings in the context. And so if you look at this example, so we do not have any order between I and NLP. Why? Because we calculate the sum between their vector representation. So we can say if we have I NLP here or NLP I here, so NLP as the first word and I as the last word, the value of these two would be identical, because sum will not, the value or the output of the sum function will not change if you change the order of the inputs. On the other hand, or in return, continuous backup word allows to use of variable length contexts. Because you calculate the sum, it doesn't matter how many words you have in context. If you consider context as 2 words or 3 words or 5 words, just you calculate the sum over them or average over them, and then you will find. So the method is scalable, so it's not sensitive to the length of the context that you define. Skipgram goes one step further, actually decouples the dependence between context elements more than what we do in the continuous backup word. Why? Because in Skipgram, we treat each context as element as an independent context. So if we have, for example, here, yeah, okay. If we have I dash NLP as the context, so what we do is that we calculate the probability of Y equal 1 given W and I as one word and P Y equal 1 given W and NLP, right? So you calculate the probability independent of, or you calculate the probability of occurring a word and a word in a context, no matter what else happens in the context. So you only care that how likely it is that word W fits to the word I in the context. And in this probability, you only care how likely is that word W fits to the word NLP in the context. Right? So that's why we are saying that in the skip graph, you treat each context element as independent context. But what would be really the impact of the context in obtaining word? Context of a word translates to its surrounding words in a sentence or paragraph. If you remember, we had the definition of context in some slides at the beginning of this lecture that we said we had an example like the cat sat on the mat with the target word cat, right? Or with the target word sat. So we can define a window over this target word, and we extract the neighboring words of this target word as context. That is the way that we define a context, which also known as window-based context. For a word like W, we consider all words in a window of length 2n+1 centered on word W as context. So the length of the window is n. But what is the impact of the sizes of the window on the word embeddings that we obtain? The point is that larger windows that you use in defining the positive and negative samples uh, tend to capture more topical similarity. And when you use small windows to define your context, your word embeddings capture syntactic similarities. Contexts can also be defined on text units. For example, words that occur in the same sentence are the context of the one word, or words that occur in a paragraph, or words that occur in the text. So they do not need to be neighboring words, but they can only be in one sentence. Because if you have one sentence in the window-based approach, and when you have one sentence, the word that occurs at the end of the sentence would have a context from the follow-up sentence, right? From the following sentence. But in sentence level context, no matter in which position, no matter where a word occurs in a sentence, you consider all words in the sentence as the context for that word. Contexts can also be defined based on syntax of a sentence. For example, using parsing or dependency tree of a sentence. In this way, you can consider long distance relations between words. And contexts of a word can be foreign words that are aligned to the word in multilingual corpus. So so you can go beyond one language. So you say, if you have one word like cat, and you have Katze in German, so just you can find like the words that occur in other languages, and you connect them to this word as context.
Word2Vec package is a software package that contains some implementation of the continuous back of word and the skipgram method. It's publicly and freely available to everyone, so you can easily download it. And if you have a corpus of texts, you can train word embeddings on it. It has been shown that skipgram in practice is more effective and also more robust than continuous back of word. It's also important to know that GLOVE is another fundamental word embedding algorithm that already exists. GLOVE is an unsupervised method for obtaining word embeddings, and it makes benefit of the corpus-wide co-occurrence of words and also local context windows. This algorithm is also publicly available, and you are free to use them to train your own word embeddings. Okay, so given that there are different types of word embeddings and different algorithms to obtain word embeddings, how should we evaluate which algorithm works better, or which algorithm yields more informative word embeddings? There are two sorts of evaluation in NLP in general, which can be used for word embeddings as well. The first one is intrinsic evaluation, meaning that you want to use word embeddings to really measure the semantic relations between words. These semantic relations can be captured as word similarity or word analogy tasks. Or you can use it in an extrinsic setting, in which you evaluate your word embeddings on a downstream NLP task. It means we compare the performance of two models that differ only in the word embeddings they use. For example, for the name entity recognition tasks, we pick up a model that already works perfectly fine on name entity recognition, and we use word embedding 1 and word embedding 2 in two different settings, in two different runs. For example, in run 1, we tried this model with word embedding 1, for example, glove, and in run 2, we try with another word embedding. For example, the word embeddings that we obtained by skipgram, right? And we check which one results in a higher accuracy for the name entity recognition task. Since the only variable in this experiment is the word, is the type of the word embedding that we use, then the higher accuracy means that that word embedding, the word embedding that we use for getting higher accuracy, is more informative than the other one. We can also use it for machine translation and measure the quality with blue score. We can also use it for the summarization task and use and evaluate the performance using the Rouge score. We can also use information retrieval and use precision recall and F1 score. But here in this lecture, we are going to focus on intrinsic evaluation. So in the word similarity task, the goal is that similar words should have similar representation. So we have a data set that is publicly and freely available, so we can download it to report our results. The input to this task is a pair of words like word 1 and word 2, and the output is a number representing the similarity level of between these two words. And in the data set, then scores are associated by some human judges, and they vary between 0 and 10. 10 is the 10 shows that these two words are highly similar. Okay, so we need a function like f that maps two words to a similarity score. But how can we calculate this similarity score? We can represent these two words by the word embeddings, and then we use the cosine similarity between these two word embeddings or between these two word vectors as a proxy for the similarity of these two words in a language. So we say that similarity between wi and wj, meaning that the input words, is equals to the cosine similarity between their word embeddings. All right. The other task is word analogy. So the main goal of the word analogy is to say that if A, B, C are given, then what is the value of the question mark? Meaning that A is to B as C to Y. For example, Germany is to Berlin as France is to Paris, right? So here we do not have any information about the relation, but just we know that Germany and Berlin are related to each other in a way that France and Paris are related to each other. For this task, there is also a data set available. The data set is named Christian's words. And this data set contains different sorts of relations like capital common countries, family relations, and also currency or adjective to adverb conversion, and also comparative, like when you have an adjective and you want to transform it to the comparative version, like easy, easier. Okay, now that we know how we can evaluate our word embeddings, I'm curious to know how we can use word embeddings in real applications. Let's say we are given a group of words and we want to represent this group of words with one vector. So normally we represent each word with one vector, but if these words are kind of related, for example, if words are common words that are used in news articles, for example, or if words are the name of countries in Europe, right? So we put this word in one set, and then we want to represent this group of words with one vector. Let's say if each word represents the name of the countries in Europe, like Germany, France, and others, we make a set of these words and then these names of countries, and we want to represent all these set with one vector. one vector as a vector that represents the name of a country in Europe. So the answer is that you can easily represent each word with its word embedding, and we compute the average over these words and these word embeddings. So if we assume that E is the embedding function that takes a word and returns uh, a vector associated to that word, then we can easily convert each word in the set to its word embedding, and then we sum these vectors up and divide them by the number of vectors that we have. So the good thing about word embedding is that we can map words to some vectors, and then we can use the algebra in vector space to play with these meanings. Another application is finding similar words. The main idea for finding similar words is to use cosine similarity. So let's say we are given word WI and we want to know which word in the vocabulary is most similar to WI. So the easy way is that we compute the similarity between WI and any word WJ in the vocabulary, right? And we pick up the word that has the highest similarity value. Additionally, when you found all embedding-based similarities, you can also filter the found words with other metrics and other criteria. For example, if you want to find the most similar noun to a word, so you can find the similarity between the given word and any word in the vocabulary, and then you rank the words in the vocabulary based on their similarity score, and at the end you pick up the words that are only noun, or you pick up only nouns, and then between those or among those words you pick up the word that has the highest value. The other application is short text similarity. So we always talked about word similarity, but what if we have a short text like D1 and D2 and we want to find the similarity between them? So the easiest way is, again, to use our embedding function. So we use an embedding function to transform each of these each word of each text to their corresponding word embedding, and then we compute the cosine similarity between all words. But in order to not get biased towards the length of the documents, we always compute the average over these similarities. We discussed that we can train our own word embeddings, but there is a question that, okay, word embeddings are something that anybody who works in NLP needs them. So why not training them and saving them somewhere, and anyone who wants to use them just load them and download them and actually use them for the neural networks. So that's why for word to wake, actually there is this type of model, this type of word embeddings are now pre-trained embeddings. So they are already available. So you don't need to train them. So just you download and use them. The first one is named word to wake that you train on. This word to wake is trained on Google News. You can freely download them. Glove has 3 versions, like the version that is trained on Wikipedia. The second version is trained on Common Crawl Corpus, and the third version is trained on Twitter. Not Twitter as the application, but the tweets in the Twitter. And there are also many other pre-trained embeddings for different languages, for different domains, and different sorts of texts. Some of them are available in fast text, for example, that you can easily get them. Okay. But since we are talking about pre-trained embedding, so just it's good to talk about some practical hints. Because there are different types of pre-trained embedding, so which one is better to use? Always try out different word embeddings. We don't know which one works best. Sometimes the performance can vary drastically with different embeddings. Look at the type of word embedding um, as a hyperparameter that you want to figure out which one works the best for your setup. You need also to consider a source of corpora used to train word embeddings. Remember that larger is not always better. Maybe sometimes, or most of the times, a smaller but more domain focused word embedding can be more effective. You need also to consider what contexts were used to define similarities. We discussed that when people use a large context, then it's very likely that word embedding capture topic similarity between words. And then people use a small context. It's very likely that word embeddings capture syntactic similarity. And finally, it's always better to use the same tokenization and text normalization methods that were used for creating word embeddings. And the main reason for this is that word embeddings are like pre-trained word embeddings look like this. We usually have a list of words or a list of tokens, and in another file we have like vectors associated to these tokens. So if we use a different tokenizer than the tokenizer that is used during training the word embeddings, it's very likely the word that we get as the output of the tokenizer would be different with the tokens that are defined in the pre-trained word embeddings. By using the same tokenizer, we kind of make sure that our tokens are available in this list of pre-trained word embeddings. Okay. Now that we are familiar with the concept of word embeddings, and we talked about the embedding function, we can connect that to neural network. So we want to use it as the input layer that receives a text and then returns vectors representing each word in an embedding space. This layer is usually known as an embedding layer. Sometimes in a similar context, it's also called a lookup table. Lookup table can have different interpretation, but for now, let's assume they are the same. An embedding layer maps a sequence of word IDs to a sequence of embedding vectors. So what we do if we have a sentence of words, like including some words, we map each word to its index in the vocabulary. So for example, if we have if for example the word hello is the fifth word in the vocabulary, then the index value of this word or the word ID is 5, and then we feed this sequence of word IDs to the embedding layer, and the embedding layer returns a sequence of vectors. So given a sequence of words or word IDs, an embedding layer returns a sequence of vectors. But how does it work? It uses a lookup table. But what is a lookup table? Lookup table is a matrix with size of the number of words that we have in the vocabulary times the dimension of the embedding dimension that we want, or the size of the embeddings. Saying that the ice word of this matrix contains embeddings of the ice row of this matrix contains embeddings of the ice word in the vocabulary. So if hello is the fifth word in the vocabulary, then the fifth row in the lookup table or in the embedding layer matrix represents the word embedding of hello. So the only thing that we need to do is to replace a word with its index in the vocabulary. So how can we do it? It's very easy. So we can define vocabulary as a dictionary, right? That takes a word and returns the index. That's it. The rest will be done by neural network.
Okay. So always we talked about the embedding layer or embedding function. Now let's look at a real example of its usage in PyTorch. So we want to see how we can define word embeddings in PyTorch. So the first of all, the top part imports all necessary packages that we need in PyTorch, or let's say the primary packages that we need in PyTorch to define a neural model and train it. So we have Torch, we have Torch neural net that contains neural net packages, and then we also have functional, which contains some functions, and we have the optimization, which is the stochastic optimizer, which contains a stochastic gradient based optimization methods. Torch manual seed is like any seed value in Python. It means that when you have random initialization, you make sure that if you run your model several times, you always get some same random values. So when you use this manual seed, you can be sure that the output of your results would be reproducible. That's why this is important here. Okay, and then we have we define a dictionary that maps each word in the vocabulary to some word ID. So, for example, hello is word ID 0 and word is word ID 1. So this is the hello word example. So we assign each word in the vocabulary to an index. Right? Then we define an embedding layer. The embedding layer is very easy to define. So the embedding is a module in the neural network package. So you define the input dimension and the output dimension. The input dimension is equals to the number of words that you have in the vocabulary. So here we have 2 words, hello and words. So the input is 2, and the output is the dimension of embedded word embeddings that we want to get. So this, if we look at the definition that we have in the previous slide, we say that a lookup table or an embedding layer is a matrix with size v times the dimension of the embedding vector that we want to have. So the number of words that we have in the vocabulary is the number of rows of this matrix, and the dimension of the embedding is the number of columns that we have. Okay? Good. So yeah, we were here. So 2 is the number of words, and 5 is the dimension of the word embedding that we want to get. Okay, and then we define a tensor. So the input to the input to the embedding layer, or to the input to any neural model, is a tensor, which is a data type in PyTorch. That you can imagine it is like a matrix with more than one dimension or 2 dimensions. So you can imagine that the tensor is like a matrix, but I mean conceptually it is beyond the matrix. But for now, we can imagine that the tensor is like a matrix. But it is important to know that the input to any neural model should be a tensor in PyTorch. So what we do is that we say, assuming that we are given word hello, we want to know what is the embedding representation of word hello. We give it to the dictionary that we have, word to index, and it returns the index that we have. Hello has index 0, so it returns 0 here. And then we have a matrix like this, or a tensor like this, with type long integers, and we give this 0 to the embedding layer, right? So to the embedding layer that is defined here. So we give this lookup tensor, which is 0, to the embedding layer, and it returns the embedding layer for hello, or hello, the embedding vector for hello. So we get the vector representation of hello, and then we can print it. Okay, if you run this is more or less like random initialization. So when you call this embedding module from PyTorch, it randomly initializes its parameters. So it's more or less like random initialization. So the value of the vectors that we get for hello embedding is totally random. There are different parameters that you can define. There are embedding layers. So, for example, how PyTorch should initialize the values and so on. So you can easily check the documentation. But the point is that since we set this seed value here, if we run this model, this script several times, at each time we will get the same vector because we set the seed value to a unique number. Okay. So let's see. Okay, let's see how can we define a neural model or neural network in PyTorch. For now, we assume that we want to define a neural model like this. So we want to have an embedding layer that takes as input Okay, so let's say we want to have an embedding layer that takes as input some texts, a sequence of word IDs. So let's say, and return as the output some embeddings, right? So this is like the embedding function that we defined in the previous slides, right? So the vector that we get here, has some dimension, like the embedding. Okay. So we only have a one layer neural network. So the input is some word IDs, and the output is some word vectors. Okay. So the best way is to define it like a class. So we define a class which is inherited from the neural network module. So because it is some sort of neural network. And we then in any neural network model that you define in PyTorch consists of at least two functions. The first function is init, that you define, that you initialize your parameters, or you define your the properties of your class, and the forward function, which does the task of the forward pass in backpropagation. So given input, it returns the output. So these two functions are fixed and you need to implement them. The init function just defines the embedding layer. So the first layer that we have, or the first and the only layer that we have. So self-embedding, so it's like an embedding, as we discussed. So the input is the vocabulary size, and the dimension of the vector is like the embedding dimension. So it is like a matrix. The number of rows equals to the number of words that we have in the vocabulary, and the number of the number of columns equals to the embedding dimensions. So, and you can get this vocabulary size and embedding dimensions as input to your class definition, right? Okay. Now, when we are given some inputs like word IDs, we can just easily call these self-embeddings and give the inputs to these embeddings, and we return out. So it's a very simple way to define a model in PyTorch, right? So in PyTorch, we define each model as a class, and then each class consists of init function and the forward function. Yeah, and
it may consist of several layers or only one layer. Okay, now that we define our embedding layer, let's see how we can get output from it. Okay, now that we define this class, so everything that we have in the top, in this part, everything that we have in this part is from the previous slide. So the new part is here in the bottom part that we define the main part of our script. So how should we call a model neural network model in PyTorch? So we define our embedding layer model, so with vocabulary size of 10 and embedding size of 3. So we define some inputs like word indexes that we want. So let's say we want to return word vectors or word embeddings for a word that has index 1 and a word that has index 5, and they appeared in a sequence like we have, for example, hello world, right? But hello has index 1 and word has index 5. So we, as we discussed earlier, the input to any neural model is a tensor. So we convert the list to the tensor, and then we give it to the model. And the model is the embedding layer, so it comes to the forward function here. It maps the input to some embedding vectors and returns that here. So you can also see the shape of the input, like what is the dimension. So since we have two words here, so we expect that we receive two vectors times embedding size is 3. So we expect to see a dimension of 2 times 3, right? We expect to see a matrix with 3 columns and two rows. This one is for this one is the vector associated with the word with index 1, and this row is the vector associated with the word with index 5. Right? So I want you to go to Moodle, and I provided the Python script in which I implemented this simple neural model, so you can easily see how it works, and you can play with that and see how you can define an embedding layer, which is like the first step of defining any neural model in PyTorch. Okay. So far, we only use random word embeddings, but we know that there are many word embeddings available in the world. The question is that how can we load these word embeddings in PyTorch? Let's assume that these word embeddings are saved in some files, right? And you load them and you get some metrics. So you load them in some metrics. So you know that index 0 is mapped to this vector, index 1 is mapped to this vector. So you have a weights matrix. So as the input, so we define a weight matrix. So before this, we only had vocabulary size and embedding dimension, and now we have a weight matrix. And the idea is that weight matrix can be pre-trained word embeddings done by Word2Vec or just GitLab or any other matrix that you have. So you load this, or just you get it as the input, and when you are defining your embedding layer, so you first initialize that randomly, and then you load this embedding in, or these parameters in your embedding layer. So you say that in the embeddings that we have, we load these weights or the parameters of the layer with the matrix that we received as the input. For example, if you here you have glove, so if here, for example, here, if you have the word vectors from glove, so you can just load them from a file, make them in a matrix,
and give it to your embedding layer when you are defining. And this one line loads GitLab vectors into your embedding layers, and everything else would stay the same. So the only difference here is that instead of using the random word vectors, you will use some pre-trained word embeddings. Okay. Now we also discussed about the freezing or updating word embeddings. When you load pre-trained word embeddings or any word embeddings, if you randomly initialize that, you can tune or not tune them. You can consider them as some parameters of your model, or you can consider them fixed or freeze and do not update them. So you have two experimental setups usually. The first one is that you assume that you can update your word vectors. And in the second experimental setup, you do not update your vector. You do not update your word vectors. But how should we implement that in PyTorch? It's very easy. So here, we say we add another parameter like freeze, which can be true or false. When it is true, it means that we don't want to, we define our embedding layer, and we don't want its word embeddings to get updated during backpropagation, right? So, so the only thing that we say that if freeze is true, self embeddings dot weights, which are, when we say weight, which this weight is the word embedding matrix that we have in the embedding layer, requires gradient equals to false. When we set this property to false, requires gradient to false, it means that our PyTorch understands that this should not be included in the parameters during a stochastic gradient descent. So when a stochastic gradient descent wants to update the parameters, it looks at parameters that whose requires gradient property is set to true, and which is the default value. So any variable or any parameters that we have in PyTorch are supposed to be updated during training, because by default they requires grad property is true, unless you set that property to false. This is what we are doing in embedding layer. So in the embedding layer, when we are defining our embedding layer, when we are initializing an instance of our embedding layer, we define it like this. So we say either we want to keep the parameters fixed or we want to update them. So this is the way that you can tell your neural network to freeze the parameters and do not update do not update the parameters of one layer. In this case, we do not update the parameters of embedding layer, or we do not update the word vectors. Okay. At the end, I want to talk about some limitations of current word embeddings. The algorithms discussed provide very little control over the kind of similarity they include. So by similarity, we only focus on distributional hypothesis. We said that words that occur in the same context are similar, right? But we do not define any type of similarity. So we rely mainly on the data. For example, in one context, cat is more similar to dog than to tiger, as they both are pets. Right? Tiger is not a pet. But cat is more similar to tiger than to dog, as they both as fleas. So the way that we are defining the word meaning and the way that we are modeling the word, the distributional hypothesis doesn't capture the type of the similarity that we want to include. And this is important because we as a human can understand the difference between these two similarities. The other limitation is that Many of the trivial properties of words are ignored because people are less likely to mention known information than they are to mention novel one. So let's look at an example. It's easier to understand an example. For example, when people talk about white sheep, they will likely prefer to use only sheep. Why? Because they assume that when they talk about sheep, authors know that most sheep in the world are white. I don't know if they are mostly white, but just it seems that the first thing that comes to mind to our mind is a white sheep. It is more or less like a background knowledge that exists, or an author assumes that um, reader reader focuses on the white sheep, right? Or maybe the color is not important here; only sheep matters, right? But the point, so when we look at texts that are talking about white sheep, they probably don't talk about the color. They mainly refer to it as sheep. But when we are talking about black sheep, it's very likely that we use the color information. So we use black as an adjective to the sheep because we wanted to focus on the color. So we want to say they are black sheep. Uh, so it seems that we as a human sometimes focus, we do not express informations that are that are likely our readers know them, and this reflects itself in our training data. If we do not see white sheep next to each other, and we always see black and sheep next to each other in the context, our model learns that a sheep is black, not so it doesn't know that sheep can be also white, right? And this is a weakness. So our model learns that sheep is black, while we as a human think the other way around, or even what we think is not important. The reality is not that sheep can be black or sheep can be white, and it happens mainly because data is not perfect. Right? Data can be even if we use a lot of data, still it's not perfect. Okay. Yeah, so a model or like a word embedding trained on texts only, or texts like this only might easily, or a model that is mainly trained on texts can easily mislead by this phenomenon. Okay. The other limitation is that text corpora can easily be biased for better or worse. So I don't want to discuss that this bias is good or bad, or this is reality or not, but this is something that exists. The data that we have is already biased. So many of the point is that we as humans can be biased, and then we reflect this bias in the data and the text, and then what as a result our model gets biased to to these correct or incorrect facts. For example, when you look at the pre-trained word embeddings, you realize that most of uh, the technical jobs are or like CEO or just like high rank jobs are assigned to men, but this is not the reality, right? This is not true. So, and why it is happening? It's because the data is biased, because uh, terms that are, or nouns that are men and that are names for men are in the context of the high ranked jobs in Texas, right? That's why the model thinks that these two are kind of related, but they are not. They are not. So there are different types of biases that are happening in the current word embeddings, like gender and racial biases are very common. So they need to be addressed. The other limitation is that current word vectors are context independent. What does that mean? I mean, the word vectors that we discussed, at least in this lecture, are context independent. So there are some advanced methods that we will discuss in the in next lecture, which kind of address this problem. But let me explain the problem roughly. But in the next lecture, we can go into the deep of this problem, into the depths of this problem. Um, in reality, there is no such a thing to have context-independent word meaning. What we discuss in this lecture is that each word is associated with a vector that represents the meaning of the word, right? But this doesn't have any meaning. That doesn't happen in reality. And as a simple example, some words in a language can have multiple sense, right? For example, the word bank. In one context, it may refer to a financial institution, or in another context, it may refer to the side of a river. So it's not clear, without having context, it's not clear which sense we mean, right? And the approaches that we discuss in this lecture, like word-to-vec approaches, glove, or count-based approaches, they all consider words independent out of their context. So they provide a meaning representation independent of the context, which is not valid. Okay, so to wrap up our lecture, we discussed about common features used for converting textual data into numerical vectors. We discussed about different sources of information that may exist about text, and we also explained that the vector representation of a text should reflect linguistic properties of the text. And these common features were kind of traditional features that people use to convert texts to vectors. And then we said these vectors so we have two types of features, like numerical features, for which we do not have any problem, and we have categorical features, which are difficult to represent. And we propose two solutions: one hot encodings and dense encodings. We discuss about the positive and negative things of each approach, and we concluded that dense encoding is better to follow for categorical features. And then we look at the word representation, and we say, okay, words in a vocabulary can be considered as a categorical feature. So each word can have one of the, or in each position, each token of the text can have one category of all words in the vocabulary. So then we discussed that, okay, if we look at each word as a categorical feature, then we can represent each word via vector or via dense vector, and then this dense vector is named word embeddings. And then how should we obtain these word embeddings? How to get them? We discussed about skipgram and continuous backward word approach, and we also discussed about glove briefly. We discussed where to use these word embeddings, like what applications, like compute, like for intrinsic evaluation and extrinsic evaluation. We also discussed about how to use word embeddings to compute the prototype of a group of words, and how to calculate the similarity between two words, how to solve the word analogy tasks, and how to use them for short text similarities. And at the end, we discuss some practical hints on how to use word embeddings. I show you how we can use word embeddings in PyTorch to define the first layer in our neural networks. So if given a sentence, a sequence of words, we can map each word to a sequence of word IDs, and then we use these word IDs as the input to an embedding layer, and then we will have some vectors. So after that, we can define any architecture that we want for our neural network. We discussed that these word embeddings can be taken as parameters of our neural network. So we can update them during training, or we can freeze them during training. So it's very easy, and we also discussed that how can we easily make how can we easily tell a model in PyTorch to freeze the word vectors or to update the word vectors. That's it. So we also discussed about the limitations of the discussed word vectors, but they are, as I said, there are these methods are not the only ways we can get word vectors, or there are not only pre-trained word embeddings. There are some advanced approaches which will be discussed in the next lecture. Additionally, we mainly talk about word embeddings, but we didn't go to beyond words. So we can have sentence embedding. We can have also a bit more specific, like character embeddings. Which one is better? We don't know. We can see that in the next lecture. That's it. Thank you for watching the video, and thanks for participating in this lecture. Feel free to ask your questions in the comments, or put your questions in the Moodle forum. We will be happy to address your questions. Thanks. Bye.